Hi everyone, I have been discharging the battery now for 24 hours and I'm using this resistor here. It's 33 ohm and the battery is it's 13 amp hours and it's hot. That's why it's resting on this plate, which is warm, and we're down to 11.82 volts, and I'm now going to switch over to charging. So I'm disconnecting the resistor and let's turn switches on and go on. Okay, so now I'm charging, but not like the way I used to do. Let's see what I've been doing. First I started out with this circuit, but I didn't want to have the current going through here at the gate also to go through the battery, because then it was hard to calculate the charge going to the battery. So I changed the position of the SCR and the battery, and I got this circuit instead. So now it's really easy to calculate the charge, and I'll show you how to do that. But what I'm doing now is I'm doing this really simple circuit, so it's I'm just rectifying the AC, and the capacitor now is more like a current limiter, and I'm not using a full wave bridge rectifier. I'm just rectifying in one direction, and there's a reason for it. Now I'll show you. The charge going to the battery is doing work, which is or you could say the energy going into the battery is simply the voltage of the battery times the charge going into in coulombs. Now usually we write this as voltage of the battery times the current times time, but we know that current is you can rewrite this yet another way, times current per time times time, and those goes away, and we have this to work with. And the charge in a capacitor being dumped is like this. It's the capacitance times the voltage, or the difference of voltage, which in my case is, I call it the voltage of the capacitor, sorry, minus the voltage of the battery. So this is the voltage change, which is times the capacitance. This is the charge for each dump, which is done 50 times a second. So here's the charge going to the battery in 1 second. So this is what I've been using when I have calculated the current to the battery. So this times voltage of the battery, this goes away, and here is the energy to the battery. Now what I'm doing now is, if you have the voltage, the AC voltage like this, and in the previous circuit I was charging here. I was charging the capacitance in the uptime there, then it was waiting until somewhere here when it dumped it to the battery. But the way it works now is that well, that's easy. It's just catching one of the flows through the capacitor, which is let's see, we have let's look like this. If we're only picking one of the half of the wave, like I'm doing now, we're charging the capacitor but not the battery in one direction, and in the other direction we're also charging the battery. So we're going from the voltage here to voltage here minus the voltage of the battery. So now we have 2 times voltage of the capacitor minus voltage of the battery as the voltage difference for each cycle times the capacitance times the frequency times the voltage of the battery. Okay, so that's what we're doing now. And the reason why I do it halfway only is because usually, not usually, but if you call it, let's oh, there it is. Usually when you charge a battery, we have current here and we have time here, we just put DC on it and we charge, but that's one side of the spectrum. But when we're doing it in the first, when we're really dumping the capacitor, we slice it up like this, and then we take this charge and instead we put the same area here, which is the charge, but on a very short period of time, which makes the power very high for a very short period of time. So we can either do this, that's one side of the spectrum, to do it DC, or we can do it with a spike. But now I'm doing something in between. The current now is like this. Here's what the current looks like now, and I want the resting part here, which up here is here, right? I want it to be rest, because then I can have a higher current which will equalize to a low equivalent DC charge. And actually I would like it to have a longer time in between, but for now I'm just trying this. But if I have had a full wave rectifier, I would have this as well, and there would be almost no rest time between the pulses, right? So I just want this, and that's what I'm trying to figure out how it's going to work. And now let's see what it looks like on the oscilloscope. Okay, so the yellow trace is the AC coming in, and the blue trace is the capacitor, the voltage of the capacitor. And the dark blue is the difference between the two, but it's on another scale. It's double scale, so it's let's see. Oh yeah, I'll keep it that way. So the difference between the yellow and the light blue is the voltage of the battery, and peak to peak, it's on the yellow trace it's 130, and then you have to subtract the value of the battery to get the voltage difference of the capacitor, so you can calculate the charge going to the battery. So that's what I'm doing now, and this will take some time to charge, maybe 3 to 4 days, and we'll see what's coming out. Now I have this voltage meter on, which is logging, so I can calculate the actual energy going from the capacitor to the battery. And what I like about this circuit, of course, is that it's very efficient this time around. The previous circuit wasn't efficient when it comes to the energy in the capacitor versus the energy going into the battery. There was a great loss there. In this case, there are no losses like that, so I'm very curious how this will turn out. And if this is going well, I'm also going to try a full wave rectifier just to check the difference. Okay, this was a longer video. Thank you for watching.